Hello everybody, this is my exam 1 video for the random questions. My name is Cash Merrill. Let's just go ahead and jump into it. So for letter A, so number 1 is talking about plant traits, and number A wants us to come up with a null hypothesis. So my null hypothesis is written here. For flower color, I thought purple was dominant to red flower color. Long pollen was dominant to round pollen. And I said these traits follow Mendel's laws of independent assortment and the law of segregation. So we have our parental cross, a homozygous dominant individual to a homozygous recessive would give a completely heterozygous F1 generation. I said that the ratios would be 9 to 3 to 3 to 1 and follow Mendel's laws here. So we have 180. For pollen, we have 60. Red flowers, long pollen, 60. Long pollen, 20. Score test here. Expected value squared. Each one of those individual variables together. 168.3 degrees of freedom. To this chi-square value in the table, and with these degrees of freedom, I had to reject the my null hypothesis and come up with a new one. So my new null hypothesis, looking at the ratios I had and the observed ratios that they had, I still think that purple is dominant to red and that long is dominant to brown. But now I don't think that these traits follow simple Mendelian inheritance. They follow a different form other than Mendelian inheritance, and the ratio would be 11 to 1 to 1 to 3. So if these were made with these ratios, you would end up with 220 purple long, 20 purple round, 20 red long, and 60 red round. But if you look at the actual values, those match up a lot better. So that was my new hypothesis for that question. Now, number 2 is about the Huntington disease, which is a dominant, the disease allele is dominant. So it's asking us, what is the probability if, so homozygous for the recessive, mates with a heterozygous female with the disease, so capital D lowercase d. And let's actually do this. So I did this cross, and so the probability that all 6 children would be affected by Huntington disease, you have to take, so you do the Punnett square, and you find that 1/2 of the children will be affected. So you have a 1/2 chance of having an affected child, and you want to see if every time out of 6. So you do 1/2 raised to the 6th power, and you come with 1/64, or 1.56%. Now letter B is asking us, what is the chance, what is the probability that 4 children will be unaffected and 2 will be affected, not depending on the order, and the order doesn't matter. So here we use the binomial expansion equation. We got 6 factorial, the number of total events, 6, with 4 factorial, the number of unaffected, times 6 minus 4, so 2 factorial, times those who will be affected, times the probability of those who aren't affected to the 4, times the probability of those who are affected to the squared, because those are the numbers of those events. And so when you do the math on that, you get P equals 23.44% chance of that happening. Now for letter C, it's asking us, what will be the chance of the first 3 children will be either all affected with Huntington disease or all unaffected? You know, the affected probability is 1/2, so the chance of all 3 children will be affected with 1/2. The chance that they will be non-affected was also 1/2, 1/8. And there really tells us to add these 2 probabilities together. Because we're asking either this or this could happen too. So you add 1/8, get 2/16, so it's 1/4 or 25% chance that will happen. Now for number 3, I'm coming over here to, I drew these on the board here. So for letter A of the pedigree chart, I got that it was X-linked dominant. And this is because I looked at it and it doesn't seem so, I'm thinking it's dominant. Both males and females are affected. And the key here is that the affected male has daughters, but not affected sons. So the affected male has one X, and he gives it to his daughters, and he gives his Y to his sons, so the daughters are affected, not the sons. So that told me it was X-linked dominant. For letter B, you can see that it also doesn't skip generations, and males and females are affected again in this one. But the key here is this son right here. So this dad gave the disease to this son, which means that it wasn't an X-linked disease, but it's an autosomal. So that's why we see it's an autosomal dominant. For letter C, I got X-linked recessive. So here we can see it skips generations. This person did not have affected parents, and this person either. So it skips generations, and only males are affected in this. So which led me to believe that it was X-linked recessive, because these females could possibly be carriers, because they need two X's to have the disease. But the male, he only needs the one X. Or he would receive the X from his mother, and he only has one X, so he would display the phenotype. So it's X-linked recessive. Now letter D here, I got its X-linked dominance once again, because we see that it's in every generation. Both males and females are affected, but if you notice here, this male only affected daughters, not affected sons. So that led me to believe that it was X-linked dominant. And this female, she can give it to, about half of each, because she's given the X, and so it's random probability if a male or a female gets it. But here we can see that that's why it's X-linked dominant. Now number four is about the number of chromosomes in an African hedgehog in the typical diploid somatic cell. So a lot of these I kind of just thought about in my head. So the first question says, how many sets of chromosomes are present per somatic cell in this organism? And the African hedgehog has 90 chromosomes in a diploid cell. So diploid, is n equals 2. So that means he would get, in a cell you have 45 chromosomes from your mom, 45 chromosomes from the dad. So he would have 2 sets of 45 chromosomes per somatic cell, 45 from mom, 45 from dad, are homologous. Now letter B, how many tetrads are found per cell during prophase 1? So during prophase 1, we know that during S phase, so each one of these chromosomes is duplicated. So this is duplicated, now has 2 sister chromatids. The red is duplicated, now has 2 sister chromatids. And in prophase 1, they line up together like this: mother, father, father, mother. Anyway, down. And they all line up like this in pairs of 4s of sister chromatids. So you would have 45 down this side, 45 down this side. So you have 45, he would have 45 tetrads in prophase 1. Letter C, how many sister chromatids are found per cell during metaphase 2? So after prophase 1, during anaphase 1, these all go to one cell, and these all go to another cell. So you split the sister chromatids in half. So you have 180, 90 in half, so you would have 90 sister chromatids. You have this column of 45 chromosomes, each one having 2 sister chromatids, making 90 sister chromatids. So how many chromosomes are found per cell during prophase 2? So you would have, after these split apart, so you will have this column in this cell and this cell. So you would have a total of 45 chromosomes during prophase 2. So now number 5, I'm going to have to clear some space here really fast. So number 5. Okay, so number 5 talks about a tetrahybrid cross in pea plants. So it says, what is the probability that dwarf, wrinkled, yellow, terminal offspring plant will be produced? So for this one, I made a Punnett square for each of the letters. So I made a Punnett square for T's. Made a Punnett square for T's. I made a Punnett square for the R's for each plant. And they're heterozygous for this one as well, so it's going to be similar to the T's because they're heterozygous. Then I made a Punnett square for the Y's. one is homozygous recessive and one is heterozygous, so it's going to be a 50-50 on this one. Then I made a Punnett square for the letter A's, which one is heterozygous and one is homozygous recessive as well. So, so the first question, letter A, says what is the probability that a dwarf wrinkled yellow terminal offspring plant is produced? So the dwarf is the homozygous recessive only in this box. So you have 1/4. And these are going to be multiplied together. Now you're going to have wrinkled is also recessive, so times 4 in this box. Yellow is the dominant, but you can see that there's half the box for dominant times 1/2. And then terminal is also dominant, and so you're also going to have 1/2. So you multiply all those together, you get 1/64 or 1.56%. Now letter B is similar, but now it's dealing with genotypes only. So what is the probability that an offspring has this specific genotype? So it wants the heterozygous, you get 1/2. Then it wants the heterozygous for R's, so that's also 1/2. These 2 of the 4 boxes. Then it wants the heterozygous for Y, which is also 1/2. And then it wants the heterozygous for A, which is also 1/2. So you multiply all those together and you get 1/16 or 6.5%. So it's just simple multiplication. Now C is asking what is the probability that the first 5 offspring have the specific genotype. So first it's asking for homozygous dominant, which is 1/4. Then it's asking for homozygous recessive, which is 1/4 here. Then it's asking for heterozygous again, which is 1/2. And asking for homozygous recessive, which is 1/2 here as well. So you multiply those together and you get 1/64. But now you have to look at it and it's asking that the first 5 offspring have this. So now you have to raise that to the 5th power. And that will give you a very small number, but it's 9.38 times 10 to the negative 8%. So a very, very small probability of that happening. Now letter D is asking what is the probability that an offspring plant will have the dwarf round yellow axial phenotype or the dwarf wrinkled green terminal phenotype. So we already know here that we're going to be adding. So to get the first phenotype, dwarf, you have 1/4. To get a dwarf here, times, times 3/4 because it's asking for round. So this gives us 3 boxes of round. Then you want 1/2 for yellow and 1/2 for axial. And that gives us a total of 3/64. Then for the second phenotype, so dwarf is also 1/2 again, or 1/4, excuse me. Then round is 1/4 because it's the recessive. Then it's asking, now it's asking for, or dwarf wrinkle, and now it's asking for green, which is 1/2, is to get 1/2 green, and terminal is also 1/2. So this is going to multiply to 1/64. Now it's asking what is the probability of getting this or this. So now you have to add it together. So 3/64 plus 1/64 equals 1/16 if you reduce, or 6.25%. So you can see that it's, when you're using or and sum, the probabilities are usually a lot higher than when you're trying to stack more things on with multiplication. But that's how you do the problems for the exam on Right On. Thanks for watching.